the main scientific portal of RCSB PDB hosted on rcsb.org, and it's a comprehensive resource designed to support the scientific community in exploring macromolecular structures. Through rcsb.org, users have open access to approximately 226,000 experimental determined structures of macromolecules, as well as over 1 million computed structure models generated with advanced AI methods. RCSB.org provide powerful tools for searching, accessing, visualizing, analyzing, and downloading these data sets with focus on data quality. Each structure's provenance is clearly identified to help users make informed decisions. And let's explore how innovations like BinaryCIF can unlock new opportunity for rapid, large-scale analysis across the entire protein data bank. Sebastian, the floor is yours.
Thank you, Jana. So my name is Sebastian Pittrich, and I'm a scientific software developer for the RCSB PDB. And one of my first projects was actually to work on BinaryCIF. And I think file formats are always integral when you actually want to, make use of the full wealth of the PDB archive. And to figure out where we are going, I think we should also look back where we came from. And more than 50 years ago, the PDB started with punch cards, so physical punch cards that described every single atom with a dedicated physical object. And up here, you can even make out one atom site record in the legacy protein data bank format. And this served us well for a couple of decades, and it's also a pragmatic solution, but it also has some severe limitations. So due to the fact that a punch card can only hold 80 characters for every single line, basically, there's strict limitations when it comes to the number of atoms that can be represented, the number of chains that can be present in a structure, and also the precision of atomic coordinates or the extent of your protein. And I would also like to mention that metadata is more difficult to handle in the legacy PDB format. And the PDB archive is not just about the atomic coordinates, but biocurators also make sure that all of the metadata is accurate. And it would be a shame to throw that away. And to solve this issue, solutions like PDBx mmCIF exist as a modern file format, but it also comes with some drawbacks. So it's still a text-based format, which is more difficult to transmit over a wire or to store. And also parsing is kind of slow for any text-based file format. And if you truly want to have future-proof access to 3D structure data, BinaryCIF is a great option. So it allows you to virtually anywhere on this globe, go on your smartphone and access the full wealth of the PDB archive in a couple of seconds by transferring hundreds of thousands of atoms to your device, or even open and visualize models like this, this model of the synaptic gap that contains around 100 million atoms. And this will load in a couple of seconds really efficiently due to the fact that BinaryCIF can compress your data without losing any of the meta information that is also associated with individual PDB entries. And to understand BinaryCIF, we should also cover CIF in a more general sense and the related schemata. And we have dedicated course material on these topics, but just to give a brief overview, I would like to mention that CIF is basically a container format where for every single file, we define a number of data blocks. So usually there's just one in the context of the PDB archive. And then data blocks contain categories, which can be accessed via a unique name. And categories are, at the end of the day, tables. So they contain different properties in different columns. Again, these columns can be accessed via a unique name. And they have a number of rows. So there can be a single row or a single value attached with every single item. And there are some categories, like, for example, atom site, that contain all the atoms. So there will be a larger number of rows that you can navigate to and then access individual values using a row index. And here I alluded or indicate different types of data. If you're dealing with generic CIF data, you don't know which categories might be present. You don't know which columns might be nested in which fashion into certain categories. And you also don't know exactly the data type of whatever value you're accessing. So you need to treat everything as a string. And PDBx mmCIF exists as a solution for this. So this is a schema that defines how CIF files in the context of the PDB archive look like. So you can for sure expect the presence of an atom site category, and you will also know which columns or properties are nested within atom site. So for example, the Cartesian coordinates in the X dimension can be accessed by a carbon X, and then you also get information about its type. So you will see that this is a floating point number because we're dealing with atomic coordinates, for example, and other types might be integer values or string values when appropriate. And I would also like to highlight a number of extensions that are built atop the PDBx mmCIF format, in particular IHMCIF, which supports integrative and hybrid structure models. And there's also ModelCIF, which is, for example, used in the context of the AlphaFold DB and provides a really convenient way to encode PLDDT confidence values without any hacks of writing those into B-factor columns or things like that. So there's a dedicated data category defined by ModelCIF, which makes it way more convenient to work with this data. And to cover some more basics, I think we should also talk about how you can compress data in a general sense and what we can learn from established compression strategies in the context of macromolecular data, because I would make the statement that in programming, it's always good to have domain knowledge, and most of the time you can come up with elegant solutions just by understanding your data or truly the problem domain that you're dealing with. And this also holds true for macromolecular file formats. So we can establish some tricks just by thinking about the data in the PDB archive. And to provide some more context, I'm sure you're all aware of different file formats that are designed to handle different types of media. So there will be file formats to handle images and audio data. And also for text data, there are different file formats. And roughly speaking, you can group them into lossless approaches, which makes sense in many cases. So for example, if you want to store the text of a book, it would be not great if you lose all of the formatting, if you try to compress it or store it, or if you lose every second page, and that would just be missing. So oftentimes you want to have a lossless representation of your data that can accurately represent all of the inputs to the last bit and byte. But on the other hand, there are lossy approaches, which can also make sense depending on your exact use case. And for example, if you transmit data over the internet or want to store image data, it can make sense to take some hit in quality for way better compression ratios. And JPEG and MP3 basically work with that in mind, that they try to exploit human perception and eliminate certain parts of your data that most humans can't perceive, especially at high quality levels. And in the context of macromolecular data, I would state that BinaryCIF is the only file format that I am aware of which truly makes sense in the context of the PDB archive, because again, we don't just care about the atomic coordinates of all the atoms, but we also want all that metadata to be present and accessible. And BinaryCIF represents or gives you access to exactly the data that you can expect from a PDBx mmCIF file, just in an optimized, more streamlined fashion. But there are also other solutions if you're fine with losing a lot of the metadata and maybe some precision for your coordinates. And with that in mind, I think it makes sense to have a closer look at the atom site category, because that's usually the largest category and also the most prominent one if you want to, for example, work with coordinates and do some visualization task or perform a computation. So this is how an atom site record might look like. So you have this definition of individual columns with a unique name. Everything is nested into atom site, and I omitted some of them for brevity. And as stated before, then you have this table with really diverse pieces of information and a number of rows, and one dedicated row describes one atom that is present in your structure. And just by looking at this data, I think you can already make out some parts that could be readily compressed. So for example, we can observe that this first column always contains the string atom, and it's just repeated a number of times. And I can really easily communicate this to you with a single sentence, and it doesn't even matter how many times this is repeated. So it can be 18 times or a million times or a billion times. There's not a whole lot of information in here, and constant data like this compresses really well with strategies like, for example, a run length encoding, where we just say that there's a certain value and it's repeated a number of times. And you can make similar observations for other pieces of information. So oftentimes you just have one value that is a constant, and it doesn't really matter which row you're looking at. Then a bit more complex. If you look at the second column, you can see data that basically changes in a predictable fashion. So we just start at 1, and then we have this running number that increments by 1 to identify every single atom in your structure in a unique fashion. And we can also define rules for that. So for example, a delta encoding is a prime example to encode data like this, or to compress it in a form that we just need to specify what's the start value, so 1 in this case, and then what's the delta, or what's the shift between every single step. So we just increment this value by 1, and then it's another example where we don't really have a whole lot of information in a particular column and can compress this. Moving on, there's also string data, which tends to be a bit more tricky to work with, but we can again observe that all of these values, there's a small set of unique values, and also just because this is the type symbol, so it's just the chemical element from the periodic table, we also know which options are present, and that most PDB entries have a really narrow set of elements that are actually present in a PDB entry. And we can readily compress this or address this by, for example, building a dictionary that would replace every of those unique strings by an integer, which already reduces the complexity of how we can operate on this data. And another nice aspect is that once we are dealing with integers, we also get access to other encoding strategies. So maybe it then makes sense to use something like a delta encoding or a run length encoding, which can be applied to integer values way more easily than it would be the case for string values. So that's like the third approach on how we deal with data in atom site. And the last case I want to point out is like the heart of the data, the atomic coordinates, which are floating point numbers. And again, we can consider what's present in the PDB archive and know that there's a limited precision that makes sense for these values, just because everything is rooted in physical experiments at the end of the day, and we have error margins, and it doesn't make sense to give like many decimal places in precision. So usually you just have 3 decimal places for atomic coordinates and 2 for some other categories. And again, we can convert this rather difficult to work with data type of floating point numbers to integers just by multiplying everything with a scalar. So if we multiply everything by 1000, we get integer values, which are, again, easier to work with. And we can also make some other observations about this data in the sense of, we also know that those points aren't randomly scattered through space, but all of these describe biological molecules, and individual atoms will be covalently bond in some form or fashion. So everything in the first residue, for example, must be somewhat close to one another. So what I'm getting at is that we don't even need to store those full values for every single row, but we could just store the value for the first row and then apply something like a delta encoding to just encode this shift of values. So we don't need to store 5 digits in this example, but we could get away with a difference that can be described in 3 digits. And this doesn't sound like a whole lot, but it actually helps us really to compress this data more and more just by exploiting this fact of all atoms being covalently bond in some form or fashion. And here you can just see another representation of what I just told you about. So there are different types of data, and we have strategies that we can apply to those data types, and those also funnel into one another, and we can try to convert everything into integer data and then get access to run length encoding, delta encoding, and something called integer packing to make it even more compact. And this might seem a bit daunting, but actually our implementations automatically select a suitable encoding strategy for you, so you don't need to worry about any of those details. And all of this is, at the end of the day, hidden from you if you don't want to deal with this. So you just get better performance for free virtually. So, and what does better performance mean? So here you can see some analysis where I'm comparing text-based mmCIF depicted in blue with the compressed BinaryCIF. And in terms of the archive size, GZIP already does a whole lot as a generic compression strategy. But if you combine it with BinaryCIF, so if you first convert to BinaryCIF and then GZIP those files, you can get savings by a factor of 2, which is really nice if you want to transfer this data. And in terms of parsing speed, you even get larger gains where parsing text-based data for the whole archive takes around half an hour, and you can cut it down to 7 to 10 minutes by using BinaryCIF, given the fact that binary data is more easy to deal with, and also we can employ strategies like lazy decoding, where most of the time you don't care about all the categories and columns, but you want to only retrieve a small number of values, so we wouldn't even need to decode all of those, all of that other information. So yeah, BinaryCIF completely interchangeable with PDBx mmCIF. You're not getting locked into any specific schema, but rather can exploit or benefit from PDBx mmCIF, but you can also do your own schema that might omit some categories or columns that you don't need for even more compact files. And last but not least, it's resource efficient. So you have smaller files, they are faster to parse, and also you need fewer resources in terms of compute to deal with this data. Number of organizations provide their data as BinaryCIF. So there's also PDBe providing access to the whole archive in the form of BinaryCIF, and also AlphaFold DB provides 200 million predictions as BinaryCIF if you know where to look. So it's really advantageous to switch to this format if you want to run any large-scale analysis. And once you get access to these slides, here you can find a number of resources. I would just like to point to this first item of models.rcsb.org/some entry identifier.bcif.gz, which gives you access to every single archive structure as BinaryCIF. And if you want to work with any of those files, this is how you can access them. And yeah, with that in mind, I would like to switch gears and actually look at some Java code and show you how you can compute archive-wide statistics in under 10 minutes. So this was motivated by one of our colleagues who was interested in the number of non-hydrogen atoms in the whole PDB archive, just as a metric of archive growth. And I think we used to have some script that was run from time to time whenever we wanted to obtain this value, but it's also really straightforward to automate this task and leverage BinaryCIF to do this basically at any point in time in a couple of minutes. So what I'm trying to do is to look at every single PDB entry and to figure out how many heavy atoms are present in that entry. And to do this, as a first step, we need to retrieve all entry identifiers. Then to access structured data, BinaryCIF can actually help with that and have less data to transfer. BinaryCIF can also help with parsing this data and make it more efficient, so we save some more time. And at the end of the day, you can do whatever analysis you want to perform on this data. So again, I'm just looking at every single entry, counting the non-hydrogen atoms and then aggregating this number into one single value. And all of this is present in a public GitHub repository, so you can check out RCSB-stats if you want to look at any of the code snippets in Java. And at the end of the day, what this project does every single week in an automated fashion is update this table and just output this number of around 2 billion non-hydrogen atoms that are present in the archive. And to that, we'll process roughly 250,000 of items in a couple of minutes. So this is how this project looks like, has a number of files, but at the heart, there's basically one Java class that is defined where all the work happens. And this class defines one method to compute those statistics. So again, the first step is to retrieve all identifiers from some public API. So don't want to go into details, but you can check out that code as well if you're interested in that. And we obtain one set of string identifiers, which are those unique identifiers for every single archive entry. And now that we have this information at hand, we can perform some work. So, for example, we could iterate or stream over this collection of identifiers. And we do so in parallel just to go fast. And I'm logging some progress because it still takes a couple of minutes. But at the end of the day, you get this stream of string values. So it's just a steady provider that gives you one identifier at a time. So we can do some work for every single identifier. And as mentioned before, the first step is to obtain structure data where BinaryCIF can help. So there's this function that takes an identifier as input and converts this to a CIF file, so a container of actual structure data that we can work with. And this is done by resolving a URL using this models.rcsb.org endpoint, and by providing the identifier for wherever the structure data lives. And then you can make use of this CIF2's Java implementation. It provides one class that has all the I/O functionality. So in here you find methods to read from certain sources, and it also provides methods to write back BinaryCIF data or text-based mmCIF, depending on what you want to do. And in here we can just point it to a certain URL, and the library will resolve this URL and load structure data. And it doesn't even matter whether this is gzip or not, whether it's text-based mmCIF or BinaryCIF. You just get this data container and then can work with this, which I think is pretty convenient. And this is pretty much all we need to do to get access to data in the form of BinaryCIF files. And now we don't have this steady stream of identifiers, but a steady stream of actual structure data where we can perform some work. And to figure out how many heavy atoms are present in this structure, we can then use this container and query it for whatever information we are interested in. And as I described before, you can do this in a really generic, kind of unsafe fashion of going to individual categories by providing a name. Then in there, you can navigate to columns by providing a name and access data in individual rows. But this is kind of unsafe. You always need to know exactly how your properties are called and how they're nested. And instead, you can also do .s and provide a certain schema. For example, mmCIF, which then provides you with types for everything. So in a file, you can then see that there will be something called atom site, a dedicated category. You can get documentation straight from the mmCIF dictionary on every single category. And within a category, you also see all the sub-columns that are present. So for example, the Cartesian coordinates and so on. And to figure out if something is a hydrogen atom or not, we have to look at the type symbol, which is a dedicated column, just contains C for carbon, N for nitrogen, and so on, which is all that we need to identify all the hydrogen atoms, to ignore those, and to count the rest. So in here, you can access values using a getter, or you could also call this values function, which again just provides an iterator over all individual rows. So we get all strings provided to us one by one. And now we can filter those to only retain heavy atoms. So in here, we just ignore everything that's a hydrogen, a deuterium, or a tritium. And at the very end, this provides us the count of all heavy atoms, all non-hydrogen atoms in every single structure. So we transformed a really complex container of structure data into a single number. And last but not least, we can aggregate this into one big sum. That is the number of all heavy atoms in a number of PDB entries. And yeah, that's all I had to you for you in terms of performing any analysis as an example of how you could go over all identifiers in the PDB archive, access structured data, do some work with that, and then perform some analysis, whatever makes sense for your use case. And with that, I would like to hand it over to my colleague Dennis Peel, who will present the the Python implementation of this codec.
Great. Yeah, I hope everybody can see my screen. And thank you, Sebastian, for that excellent overview and background of the BinaryCIF data structure, as well as the Java implementation for working with those data. I'm now going to switch gears to our using Python for interacting with mmCIF and BinaryCIF data. So the RCSB PDB maintains two repositories or Python packages for working with mmCIF and BinaryCIF data. They are listed here. The first is PyMMCIF, which basically contains all the core code for working with CIF data. And then the other is RCSB utils.io, which is basically a simplified wrapper for the PyMMCIF package. It also contains some additional tooling for working with other data objects, such as JSON and lists. And so this will be the primary package that I'm going to be using in the demo that I'll be sharing in just a few minutes. I want to also mention to please be sure to follow these repositories as we are continuously developing them and introducing new features and tools, and we don't want you to miss out on them as we introduce these enhancements. So I believe you should be able to just go to these repositories and follow them for any new updates. So before I jump into the tutorial, I want to just give a quick review of the PDBx mmCIF data structure and some terminology that I'll be using during the demo. The first of these is a data container. And what I'm referring to by that is basically the data in an entire structure file. So the data container is indicated by this data underscore prefix. And what I'm showing here is a sample mmCIF snippet from a 4HHB structure. And so the data underscore prefix indicates the beginning of a data container. I think Sebastian referred to this as a data block. It's the same thing. And most structure files just have one data container in them. You can, of course, add more, but for the most part, throughout our archive, throughout the PDB archive, it just contains one data container per structure. Additional terms to keep in mind are category and attribute. And so within an mmCIF file, there's a series of data items which are broken down into a category and attribute pair. So in this case, database 2 would be the category, database ID would be the attribute, and the corresponding value for that attribute would be PDB for the first loop and www.pdb for the second loop. All of these categories and attributes are defined in a set of dictionaries that are available at mmcif.www.pdb.org. And along with these definitions, it also contains the data types that each of the values of these attributes should have. So whether it should be an integer, a string, or a float. And this is important because our Python packages currently use these dictionaries for encoding data into BinaryCIF. It helps automatically map the data type that a particular attribute should be into the encoded type that it should be in BinaryCIF. So with that in mind, I'm going to transition to the live demo. And I know that you're just as excited to jump into this as I am, but I'm going to ask that you resist that urge and try to just follow along over the next 10 minutes because I have a lot to pack in and a lot to say, and I don't want you to miss anything. But feel free to take a screenshot of this here, and we're also going to share these links in the chat in a bit, so you'll be able to follow along on your own afterward. So I'm going to jump out of my presentation here and click on this, this URL to bring me to a Python notebook. It's in our RCSB training resources repository. And at the top of this notebook, we have this open in collab badge. And if you click on this, it'll actually open that notebook in Google Colab. And so obviously you need a Google account for doing this on your own. So if you don't have that set up, you'll want to do that. So the first thing that we'll do is just install the packages. And I'm adding this upgrade flag so that we also make sure that we upgrade them. Because like I said, you want to make sure to keep these packages up to date so you're getting the most benefit out of them. So I'm going to run this cell. It's going to warn me that this is a new notebook, but we have trust in this notebook. So I'll run this and it'll take maybe a couple seconds. And should finish up soon. All right, so now we see that check mark, so it indicates that it's done. So now I can scroll down to the to actually using these packages. So the first thing we're going to do is just read an mmCIF and a BinaryCIF file, and we can do that making use of this Marshall utility module within the RCSB utils IO package. This module basically marshals together a whole bunch of utilities for easy use of interacting with mmCIF data. So you can do things like import data, export data, wrangle data, and change the data. So let's first start by importing the data, and we're going to just provide a URL to one of our CIF files, so 4HHB. And note that you can provide either the gzip version or an uncompressed version. You could provide just the .cif file. You can also do this with a local file, so if you have a local file path. And then you want to just specify the format is mmCIF. So this is going to import the data into a data container list object. And so I mentioned what a data container was. So this is going to be a list of all the data containers in this file, which is in this case going to be just one. But so I'll run this and we see that that worked. And likewise, you can also import BinaryCIF data just very similarly. So instead of providing the CIF URL, we would provide the BinaryCIF URL. Note that this is a slightly different domain. So it'll be models.rcsb.org. And then you change the format to BinaryCIF. So you just can go ahead and run that and it loads even more quickly. And so now we have this data loaded into data container list. And now we want to start working with it and accessing that data. So the first thing we're going to do is take the first item of that data container list, because usually there's just one data container per file. And then we're going to print that name of the container. So I'm going to run this and we see that the container name is 4HHB. Likewise, we can list all the categories in this data container by using the getObjectNameList method. And if we run that, we see all the all the categories that are within that data container. And you'll see that these actually match up with what I just showed on this slide. So we have entry, audit conform, database 2, and we see we have entry, audit conform, database 2. So now if we want to access specific values from attributes in their categories, I show a quick demo here of listing the first 5 rows from the Atom site category. And if I were to run this, we see that these all get printed out. We have each of the information about each of these attributes. Unfortunately, I don't have a lot of time to go through the details of this loop, but I hope that on your own exploration, you'll be able to understand that on your own. If you do have questions, please reach out to us through our Contact Us button or through our GitHub repositories. You're welcome to create an issue if you have a question or an issue using the package. You can also take all the data from a data container and put it into a dictionary if you wanted. And so that's what I'm demonstrating here, is by taking all the data and putting it in this DCD dictionary object. And then I'm going to print the first 5 data items from that dictionary. So if I run this, we see that the first thing we print out is actually the data container name, so 4HHB. And then we have our next our next category and attribute and value, so entry, ID, 4HHB, and then our next category and set of attributes and values, and so forth. And the main reason why I wanted to show this is because you can actually do more than just work with mmCIF data using this package. You can work with dictionary data, and so that basically translates to JSON data and pickle data. So you can take that DCD dictionary that we just created up here, and you can export this into a JSON by just specifying format JSON. And likewise, you can also export it as a pickle, which is basically like a compressed version of a JSON. So if I run this, we'll see that this completed successfully. And one really cool thing about Google Colab is that you can actually see the files that you're generating. So if you click on this folder icon here and click refresh, you'll see that we've exported these files. And if you were to double click on one, it'll even show you a quick preview of it. And so we see that we basically converted this into a dictionary. All right, so now let's jump into manipulating, deleting, and adding categories. So before we do that, let's first just create a copy of the data container list so we don't mess with the original one. So I'm just going to do that. And then I'm going to take the first data container from that list, like we did above, and it'll be called DC. So first thing we can do is rename a category. So let's say we want to rename citation to citation reference for whatever reason. We can run that and it'll report true. If we were interested in deleting any categories, so for example, if you wanted to delete all EM related categories to perhaps save space and you're not particularly interested in that for your own research, you could do so using the remove method. And so we can just run this. And then you can also add a new category. So you can add a new category using the mmCIF package and specifically the data category module from that package. And so that will let you define a new category, and we'll just call it new category, and as well as a set of attributes that will go along with that. We'll say ordinal, attribute 1, and attribute 2. You can then append values to those attributes by using this append method on the new category. And then when you're done constructing that new category and that data category, you can append it to your data container using the append method here. So I'm going to go ahead and run that. And then we can check to see if all these things took place. So by printing out the category names now. So we can scroll over and we should see that citation reference should exist now. So instead of citation, we have citation reference. And if we scroll to the end, we should see that we've added a new category. You can also view this directly by exporting the data as a CIF file and then looking at that CIF file. So let's just quickly do that. And I have to refresh this, and I'm going to double click this to download the file. And let me go ahead and open that up. And so this will be our new modified CIF file. And if I look for new category, we see that we've added this category here. And also if we look for citation reference, that should show up here. So that's just kind of evidence that the changes that we applied succeeded. So I'm going to minimize that. And if you're interested in the other methods that are available for a data container, you can I've listed them here, but you can also explore them on your own in your own Python interpreter. If you were to type DC dot and then hit tab, like I've done here, it should autocomplete what the possible methods are. So we see that we have rename, remove, append. You can also print a certain data container for easy viewing. And you can also convert it to JSON this way. And if you need help on any of these methods, you can either go to the GitHub repositories directly, or you can type help, for example, dc.remove, and it should show you how to make use of that method. All right, so the next thing we're going to jump into is exporting data. And so I've already shown above that you can export data as a CIF file very easily by just specifying your output format as mmCIF, and then specifying the name of your file and the data container list object, and then saying your Marshall utility.do export. And so we can run that, and we see we get this new file here. If you want to export this as a BinaryCIF, it's a couple extra steps. And this is basically because, as I mentioned earlier, we make use of the dictionaries to determine the typing to use for encoding the data. So while you can import BinaryCIF very easily with this package, there's a couple extra steps that you have to follow for exporting data as BinaryCIF. So the first thing we're going to do is just specify each of the dictionaries that we want to use. And these are pretty much the main dictionaries that we use for the PDB archive. And then this is a model CIF extension to that dictionary. So if you're working with computed structure models, like from AlphaFold, you'll want to include this dictionary as well. And so again, sorry, I don't have a lot of time to dig into each of these specific steps, but basically we're going to create this dictionary API object and using these dictionaries. And so that using this dictionary API object, let me make sure I run this. We can provide this as input to the export command. So export method. So we're going to specify the dictionary API equals this dictionary API method or object that we created here. And so you can now export as many BinaryCIFs as you want. You only have to do the above thing once. And once you create this dictionary API object, you can reuse it as much as you want. So we've just created now 3 new BinaryCIF files. You can also compress these files using the file utility module. So you just import this from RCSB utils.io. You instantiate the module object, and then you can use the compress method to compress it into a gzip file. And then we'll remove the original uncompressed file. So let me run this, and we should see this get reflected. So now we've replaced our BinaryCIF file with the compressed version. And again, we're always developing these tools, so we're planning to add even more enhancements to them, such as circumventing the need to create the dictionary API object, as well as allowing for automatic gzip compression. So please follow along these repositories to make sure you're using the latest version of them. So the last thing I want to just touch on is working with computed structure models. And so computed structure models, if you're not familiar, are basically just AI generated structures. And so we can make use of an AlphaFold generated structure by importing it directly from AlphaFold DB. So I provided the CIF file here, and I'll run this. And then we can export this as a BinaryCIF. And we can do that using the same dictionary API object that we created above. And this is because we're using, again, that model CIF extension dictionary, which defines computed structure model specific categories and attributes, such as model quality metrics like the PLDDT score. So I can go ahead and run this, and we see that that worked. So again, if these links haven't already been shared, we'll share them in the chat in a moment. But I hope that provides a quick rundown of what's possible with Python for working with mmCIF and BinaryCIF data. So I'm now going to hand it off to Jana to discuss our remaining slides and go on to our Q&A.
Thank you. And thank you, Sebastian and Dennis, for giving an overview and sharing examples with us. That brings us to the end of our session today. But before we transition to Q&A, I would like to make a few announcements. PDB will go through a major transition, as it is anticipated that before 2028, we will run out of well-established 4-letter code identifiers assigned to PDB structures upon deposition. At that point, release structures will be identified by extended alphanumeric codes. And it's important to note that these extended accession codes are not going to be compatible with the legacy PDB file format. So if your pipelines or tools rely on the legacy PDB files, we advise you to transition to PDBx mmCIF file format as early as possible. Next. And you can join us on November 7 for a virtual hour where Ezra Pesach will answer all your questions about the upcoming transition to extended PDB identifiers. Next, please. We are seeking your feedback to understand how can we improve the macromolecular structure visualization on rcsb.org. Please take a moment to complete a brief survey and help us create better experience for all our users. Thank you for helping us make rcsb.org even better. And the link to the survey will be posted in the chat. Next, please. After we wrap up, and before you go, please share your thoughts on what worked well today and any areas where we can improve our virtual events going forward through completing the exit survey. We'll post the link of the survey in the chat. Please take a moment to open those links in your browser so you have them readily available after this event ends. Next, please. Thank you. We would like to extend our thanks to everyone who made today's session possible. This work reflects the dedication and expertise of the entire PDB team, who continually strive to advance access to structural biology data for the scientific community. Special thanks go to David Senna, Alex Rose, and the late John Westbrook, whose legacy continues to inspire our efforts. And we are also deeply grateful to NSF, NIH, and DOE for their continued support, enabling us to bring those resources to the community. Next, please. And now I would like to open the floor for questions. We encourage you to share any thought you have or any question about today's topic. And let's dive into the Q&A with the first question coming from Alessandro Barbieri. I'll read the question out loud. Many different file formats are present. PDB QT for Autodoc, mol2, mol SDF. Information is often lost by converting them into one another. Could potentially BinaryCIF store all the information so that we can perform a proper reconversion of certain programs' output in the same fashion of the original input? Sebastian, I would like to hand this question to you.
So I have to admit that I'm not familiar with the first format, but for the mol2, mol, and SDF, I would say that on the one hand, BinaryCIF doesn't make that much sense because those tend to be rather small files that describe individual ligands. So if you only have a smaller set of data, you also have some overhead of just generating the BinaryCIF container or this format. It is more relevant for really large atom site records, for example. I would say that in a general sense, PDBx mmCIF really helps with that. Like all of those formats basically have the atomic coordinates, and then you enrich them with additional information on the bond order between certain atoms and maybe charge information. And PDBx mmCIF can provide all of that in a really convenient fashion where you don't lose information. And I would also like to point out that we have a public API that allows you to convert between those formats to some degree. So on this resource slide, I mentioned something, or just wrote it down, I guess. We offer something called Model Server API, which actually works on BinaryCIF files just for efficiency. And this API allows you to make certain selections in your data and to convert between formats depending on whether you want text-based PDBx mmCIF, BinaryCIF, and you can also convert individual ligands, for example, to SDF, mol, or mol2 as a format, and at the same time enrich them with additional metadata that describes bond orders and charges and anything that is specific to those more narrow formats. So I would say PDBx mmCIF is maybe what you're looking for.
Thank you, Sebastian. And we can move on to a second question. Do you have C++ interface to read and process mmCIF or BinaryCIF? Dennis, would you take this question up?
Yeah, so the mmCIF package that we shared earlier that I was presenting on, that has C++ modules for working with mmCIF data. It does not have it for BinaryCIF. That's something that, again, please follow along for updates. But I'll share the package again on here. If you kind of dig into the module core code, you'll see that there's some C++ extensions that are part of there. So I encourage you to kind of explore through that package. And likewise, I just also want to mention, as a open source packages, we're always welcoming public contributions. So if you see something that could use improvement, and you have a natural inclination for fixing them, we always welcome community driven support. So see another question. Is one of the functions of the CIF Python package capable of executing protein structure comparison in an efficient way thanks to CIF compression to get the RMSD between two crystal solved structures? That's a good question. There is not a pre-built method for doing that, but you could certainly make use of the existing methods for like importing the data and taking the atom site records and performing your own. But no, there's not a built-in method for getting RMSD directly between two structures using that Python package. I'm sure there's other packages that exist that would be able to do that. And maybe Sebastian, you have experience with that.
I would also point to, we have APIs that allow you to do this calculation. So that's more our philosophy, I would say, that we offer this as an API that we can either use internally as an organization and also just provide to the public to compute alignments. So yeah, you might be interested in that.
I also wanted to mention that we do have a user interface for structural alignment comparison that behind the hood uses the BinaryCIF file to facilitate and speed up data processing and transmission. So in addition to the APIs, you could also explore this tool, and I'm going to share the link in the chat.
Also, Martin asked another question about versioning of BinaryCIF files. So for text-based PDBx mmCIF, we actually have versions accessible. Even you can go back in time and see earlier versions of those files, which makes sense in some scenarios. Unfortunately, we don't offer this for the BinaryCIF representation. So for the sake of, despite this being a compression format and being storage efficient, we don't bother keeping those files around indefinitely. So we only have a mirror of the current archive data as BinaryCIF. And if you want to go back to those BinaryCIF files, you could access those text-based mmCIF files and convert them to BinaryCIF. That would be helpful for your analysis, but we don't offer direct access to historical data in BinaryCIF at the moment. And thank you for the kind words.
We do have a last minute question. All right, let's take this question as last before we wrap up. So the Python Java packages provide the same functionality overall, or one of those is more developed than the other?
Yeah, so as the maintainer behind one of the maintainers behind the Python package, I'll say that the Java package is more developed. Currently, the Java package will automatically determine the data type based on like checking the actual file and determining if it's a float or an integer. Whereas the Python packages currently use the dictionaries for determining the type. So that's going to be one improvement that we'll offer for the Python package, so that it'll automatically determine the data type based on the actual contents of the file versus comparing the data categories with those in the dictionary.